Whether you're gearing up for your engineering finals, FE or PE exams, or getting ready to teach an engineering course, thanks for dropping by during my office hours. Today, we will continue the discussion of head loss, especially the major head loss. In our previous discussion, we have introduced that total head loss consists of two parts. 1. The major head loss, associated with frictional energy loss per length of the pipe. 2. The minor head loss, due to various components installed along the pipeline. While head loss signifies an energy reduction within the fluid, it doesn't denote a loss of the total energy of the fluid. The total energy of the fluid is conserved as a consequence of the law of conservation of energy. In reality, friction-induced major head loss leads to a corresponding rise in the fluid's internal energy, causing an increase in temperature. In many engineering flows, particularly fully developed turbulent pipe flow, major head loss is typically observed to be roughly proportional to the square of the flow rate. The most common equation used to calculate major head losses in a tube or duct is the Darcy-Weisbach equation. The Darcy-Weisbach equation is a formulation that connects the major head loss resulting from fluid friction along a specific pipe length to the average velocity of the flow. It applies to steady, incompressible single-phase flow that has reached a fully developed state. In this equation, L is the pipe length, or the distance traveled by the flow of fluid. D is the inside diameter of the pipe. V is the mean velocity of the flow. G is the gravitational acceleration. These are all straightforward parameters that we are already familiar with. The new parameter here called friction factor, symboled using the letter F, friction factor is a dimensionless parameter. Notably, it is not a constant. On the contrary, friction factor is a function of both the pipe roughness and the flow regime, as major head loss can be a result of both the friction between the fluid and the inner walls of the pipe, and the friction between adjacent fluid particles as they move relative to one another. Our calculation of major head loss in a fluid flow largely relies on correctly solving for its corresponding friction factor. However, before delving into the friction factor, it's essential to ascertain and confirm the specific flow regime under consideration. Based on the magnitude of a pi group parameter called Reynolds number, flows can be classified as laminar, transient, and turbulent. The concept was introduced by George Stokes in 1851, but the Reynolds number was named by Arnold Sommerfeld in 1908 after Osborne Reynolds, who popularized its use in 1883. The Reynolds number is the ratio of inertial forces to viscous forces within a fluid that is subjected to relative internal movement due to different fluid velocities. It quantifies the relative importance of these two types of forces for given flow conditions, and is a guide to when turbulent flow will occur in a particular situation. Laminar flow occurs at low Reynolds numbers, typically below 2000, where viscous forces are dominant, and is characterized by smooth, constant fluid motion. Turbulent flow occurs at high Reynolds numbers, typically above 3000, and it is dominated by inertial forces, which tend to produce chaotic eddies, vortices, and other flow instabilities. Transient flow is the status in between of laminar flow and turbulent. It is oftentimes called unpredictable flow as well. To calculate the Reynolds number of a pressurized flow in a pipe, we need to know the flow velocity, the pipe diameter, as well as the dynamic viscosity of the fluid. If the kinematic viscosity is used, we also need to know the mass density of the fluid, since kinematic viscosity is defined by dividing dynamic viscosity by mass density. The calculation of friction factor begins with the determination of the flow regime using the Reynolds number. If we found the flow to be laminar, as implied by a small Reynolds number, we will be able to calculate the friction factor using a very simple equation, F equals to Reynolds number divided by 64. This equation is derived directly from Newton's second law. The calculated friction factor F is then used to determine the major head loss HF. However, if the flow is turbulent, we won't be able to derive any theoretical equations to calculate the friction factor F considering the complexity and unpredictability of turbulences. In this case, we will rely on empirical equations that can best fit with the experimental data and observations. One of them is the Colebrook-White equation. To calculate the friction factor F, we must use a trial-and-error approach. It is an implicit equation in F because F appears on both sides of the equation. We first assume a value of F, such as 0.01, and substitute it in the right-hand side of the equation. This will yield a second approximation for F, which can then be used to calculate a better value of F, and so on. Generally, 3 to 4 iterations are sufficient to converge on a reasonably good value of the friction factor. Notably and interestingly, the choice of the initial guess of F will not affect the final result. It can be seen from the Colebrook-White equation. For turbulent flow and smooth pipes, the first term within the square brackets is negligible compared to the second term because pipe roughness E is very small. Similarly, for turbulent flow and fully rough pipes, with Reynolds number being a large number, F depends mostly on the absolute roughness epsilon, and therefore, the Colebrook-White equation reduces to a relatively simpler form that can be used to directly calculate the friction factor F. The typical values of pipe's absolute roughness epsilon are often reported for the pipe being used. Colebrook-White equation is a classical tool for estimating the friction factor F, and the value of F calculated using this equation can subsequently be substituted into the Darcy-Weisbach equation to determine the major head loss. However, there is one serious issue. The calculation process using Colebrook-White equation is complicated and tedious, especially before electronic calculators were first invented and started being used by engineers in 1960s. Hence, a graphical solution method that can help us estimate friction factors faster was definitely essential. This graph, known as the Moody diagram, will be discussed in depth in the next video. Thank you for tuning into this video. If you have any questions or specific civil engineering topics you'd like me to cover in future videos, feel free to leave a comment below. Your likes and subscriptions motivate me to create more content, ensuring you don't miss out on future updates.